Coming up is Cheng. Ted is got 20 years of experience in the identity management space. He's worked for a number of years for Platinum Technologies that got bought out by CA. And he's not mad at me for my comments about the eTrust server. I did check with him on it. And then, so he worked for CA for a number of years, and then now he's a engineer that works for Simus. And he's going to tell us all about the Simus Unified Authentication Authorization.
Thank you, Sean. At Simus, we developed a new version of Simus user management application based on the unified authentication, authorization, and user administration architecture. And today, I would like to share the architecture with you. This is the outline of my presentation. I will go over I will have a general introduction, and then I'll review the evolution of related technologies, and then I'll present the architecture. And based on this architecture, how do we provision AAA services, and how do we provision resources? And then at the end, I would like to go over two open overlays. One is a name service overlay. The other one is proxy cache engine. Okay. Authentication, authorization, and user administrations are critical components in secure enterprise computing. And as the directory technology becomes more and more mature, we would like to bring the service of the directory to the next level. So we would like to facilitate provisioning of those services in a very cost-effective manner. Okay? And we would like to develop technologies that are compatible with existing IT infrastructure. Our goal is that we like to do a good job, and when our solution is there, we slide into the backbone of the IT infrastructure. And this, user won't notice that, but they just feel good. That's our goal. Okay. In order to be compatible with existing IT infrastructure, we would like to evolve with existing technologies. And then we would like to improve the robustness of the existing technology. And for the features that are missing, we would like to enhance with our technology. And of course, this is open source and community sharing. Okay. In Linux and Unix-like systems, we need name services and PAM. This is for authentication, authorization, and for user management. Originally, the name service information is stored in flat files, like SC password, SC group, and they are not scalable. They have bad performance. And even if multiple systems share the same information, those files cannot be readily shared. They need to be copied over from one system to another. In order to improve on that, alternative name service store are available, like NIST, NIST Plus. Now we have multiple sources for name service information. Therefore, the nsswitch.com allows us to specify the order in which name service database should be consulted with. Okay. And for the pluggable authentication module, this is a pluggable authentication framework that allows us to stack authentication module together. Pluggable authentication module allow us to stack different modules together so that we can customize the authentication based on different the needs of individual applications. And the PAM also provide support different 4 kinds of service: one is authentication, account management, session management, and password management. Okay. Now the pedal approach. Directory has become very critical component in the IT infrastructure, and now they become the IT infrastructure backbone. So it's quite natural that we want to put the name service information in the directory. Look how I actually introduced 2 libraries, NSSLDAP and PAM-LDAP, these 2 libraries that provide name services and PAM services. These 2 libraries actually integrated name services and PAM framework into the LDAP directories. So this is a big step forward for Unix authentication and authorization services, because it brings the performance, scalability, and high availability of directory into the name service and PAM framework. As a result, it's very popular in enterprise deployments. Okay, this is the pedal approach. We have NSSLDAP, we have PAM-LDAP. Both are linked with the LDAP library. So when there's PAM-enabled application that need to access to the system, it goes through the 2 libraries. Once the user get into the library and the user want to perform certain operations, we can have a PAM-enabled sudo that further control the access control of the user. Okay. As the pedal approach become popular in enterprise deployment, and based on several years of deployment assignments, we realized there are certain areas that we can improve. Okay. One is a simple pollution, because NSSLDAP library is linked with LDAP library, and all the libraries that OpenLDAP depend on. And those libraries are dynamically loaded by system libc library at the runtime into the application address space. If the application also uses similar libraries, those symbols will clash. As a result, application will just crash. Okay, and for example, like a secure shell daemon. When secure shell daemon is linked with its own version of OpenSSL, then it loaded NSSLDAP, and NSSLDAP again link a different version of OpenSSL, then the daemon will crash. That is when NSSL library is built as a dynamic library. In order to resolve that issue, we can actually build the NSSL library as a static library. But when we do it that way, it avoids the simple pollution problem. But the library becomes bloated because for each application, we need to link in all the libraries into the application. Okay. OpenLDAP, the pedal approach also, the NSSL library also use many libraries, and some of the libraries are not threat safe. In order to protect the data because of non-reentrant code, pedal actually need to put, the NSSLDAP actually need to put a lot of mutexes to protect the access of the resources. And NSSLDAP is also a little bit chatty, because for each name service request, it needs to make an LDAP call to the server, at the least. But for example, if we are trying to get members of a group, and this group has thousands of users, that means we may be making hundreds of thousands calls to the LDAP server. So the entire network becomes very chatty. Okay. And it has limited caching support. For the information that we just got in the previous name service request, if there's the same request comes in, the library still need to go out to the LDAP server. Okay, hey, give me the same information again. Give me the same information again. Okay, and also, each application is linked with its own version of NSSL library. So if we have, in a busy system, each application make a connection to the LDAP server. So if in a busy system, there'll be a lot of applications try to open the connection to the LDAP server. So the connection resource is not very well managed. And there's no disconnected operations. all those libraries, NSSLDAP and PEM-LDAP, they depend on LDAP server to be there when services are being requested. So if LDAP server is not available, name service is not working, PEM is not working. Okay. And because there's no caching, there will be a poor performance if the system lies behind a network that's of high latency and low bandwidth. To address the paddle issues that we mentioned above, Arthur de Jong actually introduced the approach that he took was because we don't want to have a simple clash. So the approach he took was just to move all the LDAP related function call to a separate address space. In this case, that's NS-LDAP-D. And then Arthur actually introduced a new library also called NSS-LDAP. But this library does not link with the LDAP library anymore. It uses a new protocol called NSLCD protocol. Because this protocol is just for this application, so this becomes a very thin library. The NSS-LDAP library in this case is a thin library. The library now communicates with NSS-LDAP-D daemon through the Unix domain socket via this NSLCD protocol. Okay. But this job is half done. It only addressed NSS-LDAP, but not PEM-LDAP. Okay. So Howard actually came to this project and then provided the PEM-LDAP support using the NSLCD protocol. But now we have NSS-LDAP and PEM-LDAP both libraries, that thin libraries that speaks NSLCD protocols. Okay. The code then, the PEM-LDAP code actually gets donated back to the NS-LDAP project, and then the NSS-LDAP project get renamed to NSS PEM-LDAP project. Okay. And this is the architecture that we use for our new version of the user management tool. On the back of the for the two libraries, we are using the same library as those used by the NSS PEM-LDAP project. Those are two libraries that speaks NSLCD protocols. We use those. But on the other side, we are introducing a SLAPD server that is configured with a name service overlaid. And on the back, there's an LDAP backend and proxy cache. This design, basically, we would like to introduce client-side caching. For a system, we want to be able to cache information on the client system. And we also want to support this connected operation. Okay. Now, with this architecture that we have evolved from Paddle, from NS PEM-LDAP, and then we also introduce the SLAPD server. Actually, we inherit a lot of architecture enhancement from those projects. For example, the Paddle project introduced this distributed, scalable directory access. We got access to those. And because we use NS switch, now our solution actually is still compatible with the existing solutions. We just install a system, in the system we replace two libraries, NSS-LDAP and PEM-LDAP. We will replace two libraries. So there's no application recompilation or relinking. Everything stays the same. We just change two libraries. Okay, there's no symbol pollution. This is a benefit resulting from the NSS PEM-LDAP project. And there's no bloated library also from the NSS PEM-LDAP project. And now on the server side, because we introduced a SLAPD server, now we also have that connection sharing management that come with us. Okay. Now with the additional name service overlay and proxy cache engine, now we have additional features for this architecture. We can have local cache for hiding latency. We can have support for disconnected operation when LDAP server is not available. And in the previous diagram, we basically use back LDAP backend to go to the remote LDAP server and get information back to the system, and then we cache the information here. In fact, we don't need to use a back LDAP backend. We can also have a Berkeley DB backend to have a replicate copy of the directory in the local system. Okay? And Howard just introduced the backMDB backend. And because the architecture is flexible, so the performance enhancement, the lock-in, cache management improvement that Howard introduced in this conference, we can easily integrate those enhancements into this architecture. Okay. How do we provision AAA services with this architecture? There are two ways. For the host, you just go to the system, install it. That's it. Okay, and for the some virtual machines, we can just install the product, and then as a template, it becomes a virtual machine template. We just initiate instance of the virtual machine. And because we have slapped this server on the system, now that configuration, we can actually use LDAP client tool to manage that. Apache Studio, Directory Studio, and also the LDAP tool. We can actually change the configuration of the system. Okay. And I'll also go over the resource provisioning. We, at Cymus, we also develop a home directory overlay that allow us to create home directory at the runtime. Okay. Now this is the module we have. We can just run a command. This is already prototyped. We can just run RPM or package add to install the module into the system. And then we add some configuration to connect to this backend to one of the naming contexts. So instantiate and see which organization unit this system belongs to, just connect to it, and it's there. The service is available there. Now, we have an organization with a directory information tree there. And if we are going to provision different systems, we can provision them vertically. So if based on the geographic locations, or for the same naming context, if we need additional system to report to use the same directory node, we can actually replicate the directory there. Okay. So this architecture actually becomes very flexible, actually, because of the directory technology. It becomes very flexible. There's so many different ways to configure based on the business needs. Okay. In one of our telco customers, we come to realize, oh, actually, provisioning home directory is also very important, because we have users that need to log in from different systems. And if we have a Cymus user management module there, and they log into different systems, and they see the different home directory, and this is a problem. They can create a file here. When they log in from different system, the file is gone. So here, we have another engineer, Emily Beckers. She has actually developed this overlay. And so this is LDAP conference, so I'm not going to explain what an overlay is. Okay. So this is some configuration for the home directory overlay. Okay. In the slapd configuration, we just say this home directory overlay. We specify where to search for the home directory skeleton, and there's some security user ID control. And also the home directory, we can specify some expression. For example, if my user entry in the directory is export home Cheng, if you create a directory in the home directory, please use export home Cheng, for example. Okay, and home directory delete style. If we send an LDAP request to delete the user entry, we can specify ignore the home directory that has been created for this user, or delete the home directory. Or another approach is to archive. And archive is usually the most often used. Okay, so when we specify the archive delete style, that will be the path that the home directory will be just archived and stored in that directory. Okay. This is a flow for provisioning home directories. At first, we add a home directory, add a directory user. We send it to master directory server, and master directory server replicate the request to a directory server, another directory server. But we call that home directory server because this server is configured with the home directory overlay. And because of the overlay, you actually create a directory in that particular system, home directory system. When the user try to log in, you go through the PAM process, go through the PAM login cycle, and when the login is successful, then auto-mount, the home directory is auto-mount to the system. So in this case, it does not matter which system the user log into. The user will always see the same home directory that is available for him. And yeah. So in this particular architecture, we actually use very heavily two overlay. One is a name service switch overlay. Okay. And the other one is a proxy cache engine overlay. Okay. For the name service overlay, we basically use it to provide additional NSSCD communication protocol to the SLAPD. So actually you sit in front of SLAPD server listening to the domain socket for the request. And this is the way we configure with the service search descriptors, okay? And then this is an example, this is the rule we specify the descriptors. We can specify password alias groups and then the URL, how we are going to search in the directory. Okay. And this is an example of the configuration. Okay, in this case, we still use LDAP database so that we can go to the remote system to get the information that we need. And for the name service overlay, we configure overlay, and then we configure the service descriptor. If the attribute that we are searching is different from the attribute that is stored in the remote LDAP server, we can use that name service overlay map to map the attributes. Okay. We can configure the overlay using the dynamic configurations under cn equals config. And in this case, we can change different locations. We can change the URL to different locations so that different part of the tree will be used as the source for authentication. Okay. And in this case, for the password, and we are searching for UID, go to the remote system to find the account name for the value. Okay. So, and name service overlay give us the communication protocol, the NSSCD communication protocol capability. Now, once we get the information from the remote server, we would like to cache the information locally. So we basically use the proxy cache engine for caching purpose. Okay. Proxy cache engine, it was designed to improve the responsiveness of LDAP and meta backends. Okay. So when we get the information back, we actually store it locally. Okay. And this proxy cache engine does not function the same as the general cache mechanism. Usually, for the general cache mechanism, we get entry, we cache the entry. Right? Proxy cache engine does things differently. It caches entries and semantic information corresponding to recently answered queries. So you do a search, you remember what kind of search query that you have issued, and remember the search query. And for that particular search query, what are the entries that are returned for that query? It's remember both. Okay. Proxy cache engine actually implemented 3 algorithms. Query containment. Okay. if we already cached one search query and there's a new search query coming in, how can we tell whether this new search query can be answered by the result we already have in the cache? And then there's a cache replacement algorithm. When do we replace the entry that we cached with the new one? Okay. And then there's a consistent control algorithm. These are the three main algorithms that are implemented by the proxy cache engine. Okay. The first is the query containment algorithms. Okay. It basically decides when an incoming search request comes in, whether this request is semantically contained in any of the recently answered queries. First, when we get a search request, we want to see whether we have the cache information. And the cache containment algorithm decides whether the new search query is contained in the recently answered queries. Okay, and there's an example, and I took this example from the OpenLDAP website. For example, shoe size greater or equal to 9 actually is contained in the shoe size greater than or equal to 8. So if we already have a search query to search for something for entries with shoe size greater than or equal to 8. If there's another search query coming in that will search for size greater or equal to 9, we know that we can answer the query from the cache that we already have, from the entry that we already have in the cache. Okay, so the query containment algorithm basically provide one answer. For the new request, can I answer this request from the cache or not? Okay. And the LDAP matching rule syntax are used. Okay, when they compare the assertions for query containments. Okay, to implement query containment in that manner is a little bit more complicated. So there's simplified implementation, which is in the LDAPCon file, we just specify a list of cacheable templates. Okay. Then a query is cached or answered only if it belongs to one of these templates. In the LDAPCon file, we say only this kind of query we are going to cache it. So we specify the different such template. Okay. Instead of going through the complicated containment algorithm calculation, this is a simplified implementation. Okay. So only entries corresponding to cached query are stored in the proxy cache local database. Okay. And this local database, we can use Berkeley DB or memory map database. It doesn't matter. But meta information actually is stored in the memory. Excuse me. Okay. We just mentioned that the LDAP OpenLDAP does not implement the complicated query containment algorithm. So now we actually use template. So a template actually is just a prototype filter. Okay. A prototype filter is very similar to a search filter, except there's no values. Okay, so when there's search come in, we take out the attribute values. This is the prototype filters. The corresponding search filters are the prototype filters filled in with attribute values. Okay. And the cache replacement algorithm implemented by the proxy cache. This algorithm determines when a query or entry should be removed from the cache. Okay. And you use the LRU algorithm. For the consistency control, we are basically using the weak consistent control. For the query, we just specify a certain amount of time, TTL, in the cache. If the time expires, we just punch that from the cache. And there will be a background task that periodically check whether the cache, and then remove those expired entries, and the queries and the entries associated with the query. Okay. This is an example configuration. Pcache, we specify the underlying database. Then we specify the maximum cache capacity. And then we specify the attribute set. What are the attribute set? Okay, and then there's a max number of attribute set that can be defined. And entry limit is the limit of entry that can be stored for each query. And period is how often the background process, the background thread need to wake up and then remove those entries that are expired. Okay, and Pcache attribute set that basically specify a set of attributes and an index. Okay. And then there's a Pcache template. Let's take a look at the template here. This is an example of the Pcache configuration. We basically specify this is a proxy cache. We are using BerkeleyDB backend. The maximum number is 100,000 entries for the cache. We are going to store maximum number 100,000 entries. And we are specifying 11 attribute sets for the name services, for the password, group, lookup. These are the attribute sets that we are looking for. Okay, and then we specify 11 attribute sets, and 1,000 is for each query. We only store at the maximum 1,000 entries, and every 100 seconds, the background thread will wake up and check the expired query and the entries associated with the query. Okay, and this is an example of the proxy cache configuration. Okay, so in this work, we actually feel very good that we were able to actually facilitate provisioning of the services. And I believe this is going to be a cost-effective solution for the enterprise. Okay, and our design actually inherits all the enhancement from the NSS PEM, PADL, and NSS PEM LDAPD. All those enhancements, we inherit all those merits. And then we are able to provide modular service provisioning. And in this particular architecture, we actually introduced 3 overlays. One is name service overlay that enables LDAPD server to communicate using the NSLCD protocol. And we have a proxy cache overlay that offers client-side caching and disconnected operations. Okay. And we also have a home directory overlay that allows us to provision home directory. Okay. And for the memory map database that Howard introduced, the improvement that we get from the memory map database, we can also apply that to the proxy cache. Again, this product is not revolutionary. This is evolutionary. We took the existing technology, we try to improve the existing technology, and we introduce technology that are missing. And this is open source, and this is ready for community sharing. Thank you.
Okay. Got any questions?
As we are talking about authentication, authorization, I wonder if from a security point of view, if it's wise to have a cache. We all know the story of the administrator who got fired, went home, and destroyed data from his home location. If you cache things for an hour, why not have a caching determined by the person who owns the resource, like the user database, or is the, like DNS has caching based upon a time to live, which is provided by the administrator of the zone.
For the Pcache, first of all, it's configurable. If there's some information you don't want to cache, you don't need to provide that cache configuration. Okay, so it will just go away. Okay, and it really depends on your requirement. I mean, sometimes some information we can have a shorter TTL, so that it gets in, authenticate, and just expire it.
Anybody else?
Can you handle offline situations, or will this be a feature in the future?
Well, in this presentation, I use a LDAP backend. In reality, in practice, you can use a Berkeley DB backend. So you have a replicate copy of the remote directory. So that is readily available. The memory map database, I haven't tried it because Howard was still revising it on his way here.
Were you thinking an offline mode, kind of like what Active Directory does on the desktop or something? Something along a cache at the client?
Yeah. Like a remote directory is not available, right? Yeah. That's one of the main purposes for this architecture. We want to support it.
I'm linking those last two questions together, really. You've got a bit of a conflict in setting up the TTL, if that's your only tweak for expiring stuff. Because if you expire after an hour in order to get rid of the people you've deleted quickly, then you're killing your offline ability. Is it possible to say, after a short length of time, refresh if at all possible, but don't throw it away for a week?
Carl, you want this?
Yeah, there's a lot more features in the proxy cache. First of all, we also have a refresh timer, so you can keep refreshing. And also, when you're in offline mode, expiration stops. So whatever you have in the cache at the time you go offline stays there, so you won't get stranded. You're offline. What are you attacking?
What do you do about passwords?
Ted?
Oh,
Sorry.
I'm sorry.
What do you do about passwords? Entries that have got passwords in them and stuff like that?
It's the same as the directory technology. We are not using same passwords.
Okay.
We are not introducing anything new in that aspect.
All right. I'm just worried when users decide to change their password and you're trying to then get this information from the directory. If it's cached, you're using the old password still, if you're actually storing the password in the directory.
I think that is a short-term period, that is the issue, right? Yeah.
Thank you.
That's weak consistency.
One more question.
Will this work with Scram? Okay.
It's in product. I mean, you can just use RPM install and install it there.
When
Oh.
will Scram be part of it?
We just got a spec. We just got the requirement, not the spec yet.
Okay, thank you, Ted.
Thank you.